Since we're dealing with appointment scheduling, our initial design might look something like this. An appointment involves bringing together a patient and a doctor in an exam room for a particular type of exam. And since we'll typically need to know the owner's information when we deal with the scheduling, it's important to have a reference to the client from the patient also. So if we model our system this way, anytime we saved an appointment, it's going to scan all of these objects for changes and save them as well. So modeling it this way, the scope of our domain for appointment scheduling is much greater than it needs to be, since in our case, we don't expect to modify any of the other objects when we're creating an appointment.
Right, an appointment is basically just a list of resources tied to a particular time span. It models who, what, when, and where, but it doesn't ever need to change any of these associated concepts. As a result, we can simplify our design by eliminating most of these object relationships from the appointment class's design. Recall that for an object to be a good candidate for being an aggregate root, it should be the case that deleting that object should also delete the other objects within the aggregate. In the design shown here, if a customer cancels an appointment and we delete it from the system, it doesn't make sense that this should delete all of the associated objects.
So here's another perspective on that same model. By simply including the IDs of the related concepts rather than object references, we're able to ensure that creating and changing appointments has a minimal impact on our system when we persist the appointment. This relationship works because an appointment in the real world is really just a note that includes a place, time, and additional details. Adding and removing appointments shouldn't impact the people and places involved, and this revised design reflects this.
We do still have a bit more learning to do with this model, though. Somewhere in our design, we need to enforce certain invariants about appointments, like that they shouldn't be double booked. Our current thinking is that appointments need to include this rich behavior with regard to how they're scheduled. It's the aggregate root's responsibility to verify any invariants the aggregate may have, and in this case, the appointment is still acting as an aggregate root, even if we've eliminated the navigation properties to the other objects that it might be working with. Let's make sure we're clear on invariants, and then we'll see how invariants in our application impact our design. An example of an invariant in the real world is the speed of light, which is a constant that you just can't break in terms of the physics of the universe as we know it. Some things in your system must be true in order for the model to be consistent or valid. Other examples of invariants might be that the total of the items on a purchase order do not exceed the PO amount, or that appointments do not overlap, or that an end date on an object must follow the begin date on that object. Sometimes an invariant only involves a single object. Maybe a particular property or field, such as name, is required. In this case, we may model the system such that one can't even create the object without the required information. Our value objects are like this. For example, you can't create an instance of a date-time range object without defining both the start and end time. However, sometimes the invariants involve how multiple objects relate to one another.
In the example here, the purchase order and the individual line items would most likely be modeled as separate objects. However, the purchase order would be the aggregate root, and as such, it would be responsible for verifying this invariant. The individual line items on the purchase order probably don't know anything about one another, nor should they. So it wouldn't make sense to put the responsibility for enforcing this invariant in the line item object. What about appointments? How does one appointment know whether it overlaps another?
As we focused on these invariants and where they belong in our design, it became clear to us that the appointment didn't really make sense as an aggregate root. If you apply this thinking to our appointment scheduling context, it follows that one appointment doesn't really know anything about other appointments, but the schedule knows about such things. Let's evolve our domain model to follow this pattern and see where that leads us.
This feels like a big change to the model. And these kind of epiphanies happen when you're working on the model. But that's not a bad thing. It's not like you've wasted a lot of time focusing on appointment as an aggregate root. This is the beauty of modeling your domain, having conversations with different people, with the domain experts, because ideas like this bubble up and suddenly something big like this becomes clear. So you're not going to get it 100% right the first time. Your understanding will evolve as you learn more about the domain. And from time to time, you'll realize there are big changes that can dramatically improve your design. In the Domain-Driven Design book, Eric Evans talks about these breakthroughs in his section about refactoring toward deeper insight. This is really an important part of domain-driven design, and about a quarter of the book is dedicated to it. Let's take a look at the signs that Steve and I eventually recognized in our domain, which led us to shift our appointment aggregate to a schedule aggregate.
Originally, our solution had the appointment as the central focus of the design. I had figured it would be its own aggregate, with appointment at the root and its various properties as its children. As we've just discussed, that doesn't really work as well as I'd hoped, so now we're refactoring the design to introduce a new type, the schedule. Before we show that though, let's review the original structure and some of the reasons it didn't work as well as an aggregate in our solution.
You can see the original structure had appointment in its own folder and marked with the iAggregate root interface, which is required for it to be accessible from our repository methods. It has essentially the same properties as the later version, except for schedule ID, since there's no schedule type yet. And it has the same basic set of methods for modifying its room, doctor, time, and other properties. None of that really changed since all of those operations only had to deal with this single appointment instance.
However, when the appointment tried to enforce the invariant that appointments whose times overlap for the same pet should be marked as potentially conflicting, things were a bit messier. You see, this appointment doesn't actually have any association with any other appointments, so the only way to enforce this is to use a repository to get those other appointments for the same date as this one. Since entities don't support dependency injection through their constructor, this means an instance of the repository needs to be passed into this method. Creating this repository instance was the responsibility of the calling code, which may not otherwise have needed it. Note also that because the repository's interface is async, this method must now be async as well, even though no other methods on the appointment entity are async.
The real problem here, from a DDD perspective, is that cross-aggregate invariance should not be enforced by any one aggregate. In the case of something like a unique constraint between all aggregates, you might need to use a domain service or another approach. However, in other cases, the need to do this may indicate that you've missed an important part of your model.
Right. In this case, the whole thing that the user is interacting with is the clinic schedule, but nothing in our original model referred to the schedule itself. Since some of our business rules, like what to do with appointments that conflict, only make sense at this higher level, it made sense to introduce a change to our model, the schedule aggregate.
So even though the initial design we had was about scheduling, the schedule itself was never part of our model. Once we include schedule as its own explicit object in our model, it makes the design much simpler. Appointments no longer need to know anything about other appointments. The responsibility for ensuring that appointments are not double booked, and similar invariants, can be performed by the schedule, which is the aggregate root.
So let's see if this passes our other tests about defining aggregate roots. A schedule will certainly help us ensure that appointments don't overlap one another. When we save changes to a schedule, does it make sense to update any changed appointments? Yes, it does make sense. And if we were to delete an entire schedule, would it make sense to delete all of its appointments? Yeah, I think that would make sense also.
Yeah, I think this is the schedule for a particular clinic. At the moment, we only have one clinic, but if we imagine a scenario in which multiple clinics each have their own schedule, it wouldn't make sense to delete a clinic's schedule, but then keep its appointments floating around. So I think that works.
Great. And if a schedule exists for each clinic, then it makes sense to persist the schedule, which means that it needs an ID and therefore is truly an entity. And when we retrieve a schedule, we'll most likely be filtering which related appointments we want to look at. For example, today's schedule or this week's schedule. That would mean we want all of today's or all of this week's appointments from a particular clinic's schedule. It really does make a lot more sense to me to tie the appointments to a schedule than directly to a clinic. Now, let's see how this affects our design.